How's everybody today? So if you go into My Open Math today, you will see your test stuff there. You have two things. You've got the test itself and then the scratch paper. So like we talked about last time, for your scratch paper, it asks you to work on your scratch paper as you go along. You can use whatever scanning tools that you want. And then, once you scan that into either your phone or your computer or whatever you're using, you can upload that the same way you did your lab stuff. So make sure you do that right when you're done with your test. And you can get you do your test like you get to your other homeworks. I think it's at the bottom down here if you want this test 1 down there. But you can just, click on the calendar and click on that test 1 and it will load up. So any questions on any of that from a logistics perspective? No? Okay. Anything I can help you guys with today before you run off and work on that? You'll work on that either today or tomorrow, but I expect most of you will probably play with it today. But is there anything I can help you with today regarding that?
If you could go over the histograms and frequencies for me again.
Histogram and frequencies. Can you be any more specific than that?
That's just usually where I'm stuck at.
So but anything more particular about histograms or about frequency, or do you mean like building your class of frequencies, or?
No, like answering the questions of the frequency and histogram questions.
Okay, so like how many people or how many things did this or that? Okay,
exactly.
Gotcha. So I think we talked a bit last time about the importance of kind of separating those histogram questions from the empirical rule questions. But let's say we have a histogram, and that histogram is a number of, how about cookies? So, different people ate different numbers of cookies. Some people ate no cookies. I don't know what's wrong with those people, but some people do eat no cookies. Some people eat 1 cookie, 2 cookies, 3 cookies, 4 cookies, 5 cookies, and anything more than 5, we're going to put together in that 5. So some people eat no cookies. How about 3 people have no cookies? And 5 people have 1 cookie. And have 2 cookies. 7 have 3 cookies. 6 have our 4 cookies. I'm going to label these on here just to make it easier to read, because I'm doing it by hand. And let's say we go back to 3 having 5. Technically, that would be 5 or more cookies. So we could start with, very straightforward questions like how many, based on that histogram, how many These are cookies. How many had, 3 cookies? That's probably not a question we'd be asked, but it's certainly one we should be able to answer from our histogram. 3 cookies. How many had 3 cookies? That's the height at our histogram, our height of our bar. So, okay, 7 people had 3 cookies. But we could get a little more complicated here. How many is equivalent to what's the frequency that had, let's say, between 1 and 3 cookies. So that's got a little bit more to it. Does kind of depend on whether we are, conceptually, whether we're including the 1 cookie and the 3 cookies, and we are in this case. So between 1 and 3 cookies inclusively. But we would just add them up between 1 and 3 cookies. So, 5 people had 1 cookie, 10 people had 2 cookies, 7 people had 3 cookies. So we've got what? A frequency of 22. So 22 had between 1 and 3 cookies. We did then start to get into some more fussy language, and we could kind of mess with a lot of the language here. Say, what is the frequency of people having at most, say, 4 cookies? And that just starts to get a little more, we have to be a little more careful about our interpretation and how we are reading that question. But a lot of that came from being comfortable with that at most language. And if you tell somebody, you can have at most 4 cookies, are you telling them 6 cookies is okay? At most 4 cookies is a restriction. You've got to have at most, or you're allowed to have at most 4. Well, that means 4 is okay. That means 3 is okay. 2 is okay. You don't have to have any cookies, but you can't have more than 4. So that at most 4 cookies is the 4 and down. And if we want to translate that, at most 4 cookies is less than or equal to 4 cookies. And why don't we just say then you can have less than or equal to 4? Because that's more words. We often like to converse with few words. And at most implies the same thing. So either ways should be fine. So we'd have to add all those up. That would be what? 10, 20, 31. So there are 31 people that have at most 4 cookies. Questions about that so far before I start trying to mess with it a little bit more? because we could get a little more fun here. How about what is the relative frequency? Relative frequency of people having, let's say, at least 2 cookies. So that question has a little bit more going on in it. We do have to still identify and properly interpret at least 2. But we're not just finding the frequency, we're finding that relative frequency. So that does involve another step. So I'm going to give you a minute or so to try to decide how you would respond to that question. So our first job would be to identify where are our at least 2 cookies. Now, at least 2 cookies means, well, you can have 2 cookies. If you have to have at least 2, well, you could have 3, you could have 4, you could have 5. It's like, please take at least 2 cookies. Okay, take 2. And please take at least 2 cookies. You can take 7 cookies. That's at least 2. So our frequency of at least 2 is going to be that sum, which is what, 1026. But we want the relative frequency. Relative frequency. How do we find a relative frequency? How do we find a relative frequency?
Don't you add them up and then divide how many there are?
Yeah. So we take that raw frequency, so it'll still be that 26, and then divide by, well, 26 out of how many? It essentially turns our frequency into a proportion. So, you know, that 26, was that 26 a lot? Is it not very much? It puts it into perspective relative to how many we had. So we'd have to know how many we had in total. And I think the total was what, 34? 10, 20, 31, 34. Yeah, 34. So that 26 out of 34 gives us a relative frequency. And we would either want to reduce that if we want to leave it as a fraction, or get a nice decimal approximation for it. So what is the decimal approximation? Anybody have it for 26/34?
It's about 0.77.
So 0.77 up there, it's, I got a 0.765. It really should be either in that proportion form, or if you wanted to say 76.5, you have to put the percent after it. But relative frequency, we really should be in the habit of expressing it as a proportion. But if you wanted to say it's 76.5, just make sure you say 76.5%. And that's what I mean by it puts it in context. You know, how many people had at least 2 cookies? Well, 26 people did. Well, is that a lot? Is it not very many? I mean, how many is 26? Well, it's 76.5% of people had at least 2 cookies. Oh, okay. So, you know, a fair amount did, a lot more than half, but certainly not everybody.
How did you find the 34?
Added up all the individual
Oh, okay.
frequencies. And if instead we'd have had this same data in a frequency table instead, which is certainly possible, we could have had 0, 1, 2, 3, 4, oops, or 5. Did not give myself enough space. And 0 happened 3 times. Frequency, cookies. And then 5, 10, 7, 6, 3. We can answer these same questions from either a frequency distribution table. Sometimes they just call them FDT, frequency distribution table. Or we could answer these same questions from a histogram. It's the same information, just one is displayed simply numerically, the other one is displayed graphically. In the frequency distribution table, adding up their totals is more natural. We're used to finding relative frequency from a frequency distribution table, but it's important to know that we can find relative frequency from a histogram as well. We just have to add up all those frequency values. Christy, does that help? Did that get to some of the things you were talking about? Is there anything else in there that you were looking at? Okay. If something else comes up, let me know. But those are the types of things. Probably the most common type of question we've seen in those is that, you know, what is the frequency, or how many were at most or at least or less than or greater than. But we could certainly, you know, certainly find ourselves having to find either one of those depending on what we're doing. Anything else you guys would like to look at?
The interquartile range.
Okay. So if we're trying to use it or trying to find it?
Both.
Both. Okay. That's extremely reasonable. So interquartile range is a position-based argument. So whatever data we're working with in our for interquartile range, if it's not naturally ordered, we should put it in order. So I'm going to give us an ordered set of data here, just to make it handy. Again, if it's not ordered, just put it in order. If it's a long data list and putting it in order is a little bit of a pain, then we could certainly, you know, make an Excel do it for us. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Doesn't matter how many it is. Let's just use 9. So we got a data set of 9 there. We certainly should be comfortable finding the mean and standard deviation of that data set. You won't have to find the standard deviation by hand. You can use the calculator or Excel. You know, feel free to find it by hand if you want to, but you don't have to, and I certainly wouldn't. By hand is kind of long and annoying. It's important, you know, we went through it because I think it's important for us to know how to find it by hand and what it represents. But in practice, even with a fairly small data set, using the technology to find standard deviation is nice. But when finding our interquartile range and median and our 5-number summary, really that all comes down to our 5-number summary. Having the data in order like this is handy. So the first thing that's nice to find is that median. That median will help us find those other quartiles so we can find the interquartile range. So in this data set, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. So we talked about last time a little bit. Take 9 plus 1 divided by 2. 10 divided by 2 is 5. So that 5th data point is going to be our center. So 1, 2, 3, 4, 5. That 10 is going to be our center. So that would be our median. But for sake of argument or sake of our discussion here, okay, that's just not convenient. Let's say there weren't 9. Let's say there were 10. Let's say we add another data point here. Let's say that data point is 28, big data point. Then we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So where's our midway point? 10 plus 1 divided by 2 is 11 divided by 2 is 5.5. 1, 2, 3, 4, 5.5. That means it's going to occur between that 10 and 13. So what do we do with that? That 10 plus 13, 13 divided by 2, 23 divided by 2 is 11.5. So our median there would be our 11.1. So this can be a nice tool, whether you have even or odd. You just have to make sure you're interpreting it properly. That breaks us down into a lower set of 5 and an upper set of 5. Well, if we were sticking with the other problem that only had 9 points where the 10 was our median, we'd exclude the 10 and have these lower 4 and the upper 4 that didn't include the 28. But since this is an even set and our median happened in between, we can break it into 2 sets without having to exclude any data values. Those are each length 5, so our median is going to happen again in the center. And we could go off and say 5 plus 1 divided by 2 is 6 divided by 2 is 3. So it's going to be the 3rd data point in each of those lists. But once you get down to a small number like 5, it's fairly easy to see. But again, the point of the median is it should break us into 2 sets, 1 lower, 1 upper, that are exactly the same length. Because this is odd, we have to exclude that center to do that. But still breaks us into 50% below, 50% above. So our first quartile is that median of the lower set, so 9. Second quartile is the median of that. Well, the second quartile is actually just the median. The third quartile is the median of that upper set, the 15th. So if we wanted to list our 5-number summary, that's our min, our Q1, our Q2, our Q3, and our max. You'll often see, by the way, the minimum listed as Q0 and the maximum listed as Q4. We have those middle 3, the 11.5, the 9, and the 15. And we would like to think that the minimum is going to be our 5 and the max is going to be our 28. But we do have to be careful that those are not outliers, because our minimum and maximum, as you recall, are our minimum non-outlier and our maximum non-outlier. So we have to check and see, is the 5 and the 28, are either of those outliers? If they are, they can't stand as our max or our min. And this is one of the places where that interquartile range comes in. That interquartile range is supposed to give us our sense of spread based on position. So that interquartile range is essentially, it's where that middle 50% of the data lives. This middle half of the data, lies between 15 and 9. So that middle half of the data goes over that 6-unit range. That range inside our quartiles is 6. So from the perspective of how do we find our interquartile range, that's how we find our interquartile range. We do have to find the quartiles first so we can subtract them. Hopefully you've been looking over your box plots. Box plots, like, we have mean, standard deviation, and histograms. Those are all kind of value-based graphs, value-based arguments. Our median, our interquartile range, and box plots are our position-based arguments. And box plots are actually really common out there in the world. So our data ranges from small numbers around 0 up to values as big as 30. Not quite 30, but I'm just giving myself a number line here. Our median was at 11.5, so our median was at 11.5. Our first quartile was at 9. Our third quartile at 15. So that gives us where that middle is. And then we're going to go out as a whisker. This is a technical term, so whisker, down to our minimum, which looks like it'll be that 5. And then this whisker out to our maximum, but it'll be our maximum non-outlier. So we'll have to see if it's that 28 or not in a minute here. But this box plot, its job is to visually break up our data for the, into little quarters, into little 25% pieces. So 25% of our data is between 5 and 9, 25% of our data is between 9 and 11.5, 25% is between 11.5 and 15, and 25% of our data will be between 15 and whatever that max ends up being, whether it's the 28 or the 16, we'll see in a second here. So that interquartile range telling us how broad is this inner box is supposed to give us a sense of spread. Fair. How do we tell if either the 5 or the 28 are outliers? So knowing where to start and stop that min and max. To be an outlier, you're either past the third quartile plus 1.5 interquartile ranges, or you are Q1 minus 1.5 interquartile range. So essentially we're going from the outside of that box and going, okay, how far out are we going to allow data to be before we start calling it extreme data? How far out into that whisker are we going to allow ourselves to be before we start calling you extreme. And you might think, well, what happens if there's a lot of data out that far? Well, if there was a lot of data out that far, it would pull that Q3 out towards it. So if there's a lot of data, it doesn't end up often being an outlier. But if there's just a one or two or a few really extreme data values, we want to be able to say, hey, okay, that's not where most of our data is. That's just some, extreme crazy stuff going on. So to find those thresholds, we just have to compute those. So from the Q3, 15 plus 1.5 times our interquartile range, which is 6. So 15 plus 9 is 24. So that threshold of 24, that 28 is bigger. So that 28 is an outlier. Down here, that Q1 is 9. 9 minus 1.5 times 6 is 9 minus 9, 0. So that 5 is safe. And 5 isn't past 0. So that 5 gets to be our min, and it is where that whisker ends. But our threshold for large outliers stops at 24. So somewhere here at 24, anything past 24 is an outlier. So we can't say that that max is 24 and the main, or is 28. And the main reason, if you imagine, if I put this whisker out here to 28, then people would think, based on this visually, that our upper data is spread out in this region between 15 and 28. And that's simply not the case. Our data is really collected between this, between that 15 and the 16. Our data is more in these teens. We let this go out to 16. With this one extreme value up at 28. And we do want to mark that. We mark that on our box plots with either an X or an asterisk. Usually it's an asterisk, but we mark that, yeah, there's a value out here at 28, but most of our data is in here. That 25% of our data is in here with just this kind of one freaky point out here at 28. So that maximum would be our maximum non-outlier. That maximum actually ends up being 16. So we do have to be a little careful. Now, you might be looking at this and going, well, I'm saying 25% of our data, it's only these couple of points. This is a fairly small data set. If you can imagine, we had a data set of hundreds of points or even thousands of points that were all between 5 and 16 with just this one value up here at 28. The idea of not wanting to make people think there's all this data in between there seems a little bit more sensible, I think, than just this small data set. But these tools, keep in mind, are really meant for very, very large data sets. Who asked about this? I don't remember. There's not very many pictures up here today.
So we don't need to use the z-score to find the outliers?
No, really, outliers should be an interquartile range argument. For the z-scores or for our standard deviation arguments, I'll tend to stick with the language of being unusual outside of almost all. You'll never hear me, other than addressing something your book is saying, using value arguments for outliers.
Okay.
Your value arguments should be whether you're typical, unusual, or outside of almost all. Just to help clarify, and really in practice out there in the field, that's more standard. You know. Who did ask this? I don't remember. Was it Nathan? Gerald? I don't remember.
Wait, what?
I'm trying to remember who asked about.
Oh yeah, yeah.
this-
It was me. It was me.
Did this help make that make sense?
Yeah.
Okay.
Thanks.
I had a question on IEP. I'm not sure what IEP is. Am I allowed to use notes on the test? No, you shouldn't use notes on the test. You can use your calculator. You can use Excel. Shouldn't be using notes. On IEP, and I don't know what IEP is. Okay. Let's see. Oh, and if you have time things, send me a message and I can set those up for tests. So just let me know. I can check. But yeah, send me a message and I can check those values and make that setup.
Can you do some Z-score problems?
Sure. Let's kind of, you know, a fairly common question, actually, given a data set with a mean of, let's say 32 and a standard deviation of 4. Find the Z-score for, about 21. So I'm going to say for a value. So if you remember how to find a Z-score, just start doing that. But to remind you guys what our Z-score means, Z-score is the number of standard deviations above or below not two L's and below, that would be below, above or below number of standard deviations above or below the mean. A value is not a great sentence, but that's okay. So for example, as a fairly straightforward example, if your mean was equal to 10 and your standard deviation, and your standard deviation was equal to 2, then the value of 12 would have a Z-score. Well, 12 is 1 standard deviation above the mean, so it would have a Z-score of 1. The next value of 14, or a variable value of 14, would have a Z-score of 2. 8, that's 1 standard deviation below the mean, would have a Z-score of -1. 9 is half of a standard deviation below the mean, it would have a z-score of -1/2. Negatives meaning you're below the mean, positives above the mean. If we need a formula for that, which we do, our formula for that, how do we know how many standard deviations this 12 is above 10? Well, you looked at their difference. That 10 minus 12 was 2. So that value minus the mean. We went, oh, that's only 2 away. Well, how many standard deviations is 2? Well, 2 is 1, 2. Divide by that standard deviation, it'll give you how many of them that is. So if we want to find the z-score for 21, the z-score for, I'm going to put z-score for 21, take the value, 21, subtract the mean, 32, divide by the standard deviation, 4, and that's going to give us our z-score. The difference on top tells us how far we are away from the mean. That would be what, 11? Negative says we're below the mean. 21 is below 32. But how many standard deviations is that? Okay, well, we divide by 4, and it tells us how many standard deviations it was. Now, -11/4 is perfectly fine if we want a fraction, but what would that be? And if we try to turn that into a decimal, that'd be what, -2.75? If I got that right. So if we're just asked to find the z-score for 21, that z-score for 21 is -2.75. Now, if we're then asked to interpret that, what does that mean? Does this mean? Different kind of mean. What does this mean? Or how about what does this say about 21? Well, it certainly says it's below the mean. Because it's negative. Also, it being more than 2 means it is an unusual value. Because it is more than 2 standard deviations away. So this is an unusually low value for this data set. But it's not 3, so it's still in the range where we'd expect all the data to be. So I might even add that. Still in the expected range. So how this might come up as questions, you might even, commonly you'll be asked something as straightforward as, is the value of 21 unusual, yes or no? In this case, since our z-score is more than 2, yeah, or has an absolute value of more than 2, yes, it's unusual. If our z-score was less than 2, then no, it wouldn't be unusual. We could be asked for the given data set. This is less a z-score specific question, but for the given data set up here, for this data set, what range would, it says we expect all the data to fall in. Or at least almost all the data to fall in. So this is a not uncommon thing to have to do. Sometimes we don't know what the range of our data is, you know, how big and how low our data gets, but we do have averages and standard deviations. Okay, what does that tell us about what our expectations should be? We know our typical data, about 68, 70% of our data, should land within 1 standard deviation. Our data should usually land within 2, 95% of our data within 2. How many standard deviations do we call almost all of our data?
2.
Well, 2 is the usual.
Oh,
That's only 95% of our data. If you go out one more to 3 standard deviations, there were 99.7%, right? That's the almost all for our data. So, you know, within one standard deviation is our typical data. That's the middle 70%. 2 standard deviations is our usual. Or 95%, but there's still 5% of our data outside of that. It's 5% of our data that we consider to be unusual data. It's data that happens. It happens all the time. There are, like, I am unusually tall. I'm outside of 2 standard deviations from the mean of height. I'm not a freak or anything, but at 6'2", I am considered unusually tall. But 3 standard deviations, that's our almost all. Now, are there people outside of 3 standard deviations of height? Sure. But that's an extremely small percentage of the population. And most of them play basketball. What'd you ask? Sure.
I can't see what you wrote down below. Did you write anything?
Oh, no. I was writing over here.
Oh, okay.
So 3 standard deviations are almost all, 99.7%. And in a lot of practical problems, that will be all of your data. Yeah, maybe you'll have some really crazy data. But oftentimes that is everybody, depending on how spread out your data is and how much data you have. So given our data set, what range would we expect all of the data to fall in? All of the data should fall in roughly 3 standard deviations from our mean. So if we wanted to find that range would be our 32, our mean, plus or minus 3 standard deviations. So 3 times 4. So 32 plus or minus 12 is going to give us a range on the high end of 44 and on the low end, what, 20. So we'd expect all of our data to be within the range from 20 to 44. Yeah, there might be some weird values outside of that, but they'd be fairly unique values. Our range of all or almost all of our data should be in that range. And this is actually handy in both directions. If we have a mean and standard deviation, we can figure out what this range is. Also, if we want to figure out what kind of a guess at what our standard deviation might be, we don't have enough data to actually calculate our standard deviation. But if we knew this was our range, then taking the actual range, remember the range is the upper minus the lower, So taking that range of 24 and dividing it by 6 should get us back to our standard deviation. So it's a surprisingly common tool. If we have, and we'll use that a bit in chapters 7 and 8, mostly chapter 8. If we don't have any other way to figure out what our standard deviation might be, kind of a brute tool to approximate our standard deviation is to take that range and divide into 6 pieces. Those 6 pieces will be our standard deviation in length under a number of assumptions, and it's a pretty gross approximation, but sometimes that's all we've got. So that might have gone a little off on a tangent from the conversation on z-scores, and we'll use z-scores a lot, but I don't want to overcomplicate the idea of z-scores. Z-scores really is that formula, and its entire job is to tell us how many standard deviations you are from the mean.
Thank you. That helps a lot.
Sure. Okay.
I have a question about the lab.
Which one?
Lab number 2, that's due tomorrow.
Okay.
So I'm using a Mac, and a lot of the calculations were easy enough to kind of figure out, like you've been teaching us how to do it by hand and stuff. And so I actually went through and did that. And then because I wasn't able to get the table downloaded, my platform looks a lot different than the Windows platform. So
Right.
I went through and I actually tried to figure out how to download it in a different way, and I'm just not sure which tool is the right one. They have a lot of them when you look it up, so I just got a little lost on that part. But as far as the actual calculations and everything, it makes sense. I just don't know what to do about getting that table.
That is a good question. Let me look at how that's organized. Hold on a second. Now, are you using Excel for Mac?
I believe so. It's the one that I downloaded from the school's email. So I think it's for my computer. I'm not sure.
Oh, so are you referring to the add-on for the?
Yeah, exactly. It's just my
Gotcha.
platform looks 110% different. And
Yeah.
I found ways that I can look it up. I Googled it for a while. And then when I type in that kind of similar tool, it just gives me a whole long list, and none of it's the same name as what you're talking about. So I just got a little lost there.
Yeah, trying to use that data analysis tool, on a Mac.
Yeah, it's just been super funky, and I've spent a few days trying to research it. And so I was like, all right, I feel like I need to just ask at this point.
Yeah. Well, my initial responses to that would be twofold. One, the nice thing about the data analysis tool is we don't actually need it. The benefit of the data analysis tool is it will give you a whole bunch of information all at once. And it
Yeah,
gives you,
'cause
go ahead.
you had taught us how to calculate most of the information in there. So I went through and did that without having the tool. And so I just was like, wow, it would make it a lot easier to just put it in and have the tool put it out like that.
Well, there are tools in between those.
Oh, awesome.
And those are probably the tools that I would recommend. And I can send you a thing that has more of those tools on it. But let's say we had a data list. Let's say we had a data list, and you wanted to find any of those descriptive statistics, like you want to find standard deviation. Certainly don't do it by hand. If you just start typing, you'll see either stdev-p for population or stdev-s for sample. And we
Okay.
can just highlight that and select your data. You should put an end parenthesis out of habit. But using those tools to find, even the median does have a nice median tool. And then highlight the data. Okay, the median was fairly obvious, but still, when it's a big data list, it's nice to be able to have it pull up those.
That would make certain problems so much easier, actually.
Absolutely.
I'm waiting to get like a calculator, so I've just been trying to do everything on my phone. And I know you mentioned being able to do work on Excel too, so
Mhm.
this kind of explains how to do that. So thank you.
Sure. One of the things I would warn you guys about is the quartile tools in Excel are a little bit weird. It has a couple of them. It has one for excluding and one for not excluding. Essentially, Excel, it's not written by stats people for stats people. So it's there are a couple places where it's a little bit funny. And in finding the first and third quartile, it can be a little bit weird. One of the things that I tend to recommend doing, even if you have a big, long data list, put that data list in order. As soon as you do that, you can break your lists into a lower list and an upper list, no matter how long they are. And then instead of using the quartile tools, use the median tool on your lower list and your upper list. That will find your quartiles correctly. No matter whether, because if not, you have to use the right quartile tool with the right number. Like if it's an even one, you've got to use the not exclude. If it's an odd one, you have to use the excluding tool. It's just a lot more complicated. So using the median tool on your list avoids all of that. So if you've been fighting with Excel and quartiles, you should be, because Excel doesn't do quartiles great. It's a nice way to handle it. Just a little word of caution there. But yeah, that data analysis tool can be nice, but it's, in some ways, it's often more than is necessary. And it's almost always more work than is necessary.
Okay, awesome. And so my last question is just, if I can't get that tool, can I submit the lab without it? That was kind of my other fear, is not
Yeah,
having it.
just use those individual tools.
Okay, thank you.
And I've got a different Excel document that has those tools on it, more kind of broken up. If you would like that, let me know and I'll send that out.
Yes, please. I can shoot you a message too, so it's easy to know who
Perfect.
you're shooting it to. Cool.
Yeah. All right. Anything else I can do for you guys today? I'll look at that. Look back at that test and see if there's anything that makes me cringe. Think maybe I should make sure they think about that. I don't think there should be. Talked about that last time. Yeah, there are a number of questions on there where you need to write out some text about, what's your population and what's your sample and those types of things. Make sure you do remember that it will score all of those as a 0 until I have a chance to go in and grade them. So don't look at those and go like, why is my grade so horrible? It just hasn't been graded yet. So don't let that freak you out too much. Z-scores and frequency data tables. Yeah, we talked through that. I don't know. I think you guys are in good shape.
Are there going to be questions about like continuous data and just the different types as well, like categorizing?
Not very detailed, no. There are like some of the questions where you're writing stuff out, like what your data is, including information about it being, you know, qualitative or quantitative or whatnot, would be handy, but not some of those come those questions like, what is this continuous or is this discrete? And partially because, as you recall, those questions were so dependent on how you define things, that is just so much an argument question as opposed to a technical question.
Okay, awesome. That's why I got a little nervous. So thank you.
Mhm. They're good questions, but really not in this format. If I was doing a normal hand test, I would have questions like that on there because it would be about the arguments that you're making. But in this format, that's just too persnickety, if I'm allowed to use the word persnickety. Do make sure as you're working, you do write out as much as you can what you're doing on that scratch paper, and do make sure you send that scratch paper in. That is part of the test. Even if you're just writing out, this is what I put in the calculator. If something goes a little bit wrong and I'm looking at just a number, that number is crazy. I don't know where that number came from. I can't help you with points. But if I look at your scratch paper and you said, this is what I put in your calculator, you go, oh, I see the mistake that they made. That mistake makes sense and says they know this much about it. Okay, here are some points. You know what I mean? So, you know, having stuff on that scratch paper is generally very helpful. It does take mean I have to go through it all, but better that than you guys not getting any partial credit for anything. Does that all seem reasonable? All right. Well, then go take the test. What are you still doing here? As I said, you don't have to do it today. You can do it today or tomorrow. Certainly, if you do take the test, don't talk to each other about it. There is a little blurb on there. By starting the test, you agree to abide by all these, good moral decisions. But usually you guys who are taking stats, you're going to be using stats for some of the things you're going to be doing. Understanding this material is important. So hopefully you guys, have that motivation to, do this thing right so you guys can learn. So I'm not too worried about that, but just make sure you're good. Okay, anything else before I let you guys just go take that? All right.
Is there a time limit?
Yep, hour and a half.
Hour and a half. Cool.
Okay, well, go have fun. If something comes up, let me know, and I'll see what I can do for you.
Thank you, Mr.
Thank
Henry.
you.
Mhm.
Thank you.